Yeah, I got it. Program the stable. I think one grain.
Yeah, I know really. Yeah.
Okay. Let's see. Yeah. Before I get started, does anyone have any questions? It's too much light. Can you turn off the light over there? Yeah. I think that's better, right? People in the back. Yeah. And I don't know if there's anybody on Zoom, but if there is, can you hear me?
Yes.
Okay, very good. Thank you. All right. So today we will continue our discussion of the basics of quantum computers. We'll finish up the measurement section, introduce a few more, or in particular, I promised you a quantum bomb detector. So we're going to discuss that today. And then we'll go more into the math of quantum states and mapping to the block sphere and introduce, I don't know if we'll get to it today, maybe single qubit gates. Okay, quickly, you may recall from last time that that we have this block sphere, and that when we take any general state like this one, we can map it onto the 0 or 1 stage by measurement. And that quantum measurement principle says that a qubit is always found in the basis that you're measuring, say 0 or 1, with some probability. That probability, as we discussed, is given by the amplitudes or coefficients in front of these and norm squared of that coefficient. Okay, we discussed normalization. We're always going to require that a valid quantum state for a qubit should always be normalized to 1. That is, the sum of the probabilities should add up to 1, which makes sense. We want the qubit to always be found in one of those two states. We demand that physically. And we did an example last time where we ran into a little bit of trouble at the end, where I showed you that you can choose anything as a basis, some two states, as long as they're antipodal to each other on the block sphere. So this was A and B, and we ran through the math. Then I got stuck at the very end where it seemed like the probabilities didn't add up to 1. Did everybody spot Waldo in that photograph I sent in that picture? So hopefully you know that the math was correct. It was just at the very end that when I was taking the norm squared of one of the coefficients, I didn't do it correctly. So the state that we wrote down was correct, and which reminds me to avoid this problem in future. This time I brought my sheets with me in case I run into problems again today. So if you're still confused, please let me know. I can tell you about it after the class, in office hours or something. But if not, hopefully everybody was. You can watch the video and see that the math was correct. It was just the very last step where I was taking the norm squared that I made a small mistake. Okay. Okay, and you may recall the last time we discussed consecutive measurements. And in consecutive measurements, we measure along the z basis for the same qubit state, let's say A times 0 plus B times 1. And we'll get, let's say in the first measurement, we got a 0. And then if we measure along the x basis, we might get a plus, let's say, right? Because 0, as we saw, could be written as an equal superposition of plus and minus. So you could have a half probability of getting plus and half probability of getting minus. But now when you, let's say you got a plus, then when you measure in zero along the z basis again, you don't always get back a zero, right? Even though initially you started with a state that was in state zero, this time you could end up with a state that is in a qubit that's in state one after the second measurement. And this, of course, you know, taking a tip from the internet, I said, this is one weird trick to fix your classical mind. Okay, you can fix it by just thinking about this one fact repeatedly. Every time you think, oh yeah, I understand everything here, just go back and think about this one weird trick, because then it'll blow your mind all over again, right? So yeah, anyway, we talked about this, but now I'm going to make it even more, you know, I won't go through this again. I just said that. And so we will see today that actually this weirdness can be useful, right? Ultimately, we are trying to build quantum computers, and this is our first example now that you've understood a little bit already with this little basic knowledge now that you have about qubits. We're going to see that this can be useful in a somewhat interesting but contrived example, but it's still kind of, I think, interesting and useful, and you should know about this nice result. Okay, so this is the quantum bomb detector, or it's called really the Elitzer-Weidman. I may be mangling their names. Bomb experiment. Okay, so obviously the reason is it was proposed first by those two people in 1993. So the idea was they came up with was, imagine you have a box and it has a single photon detector. That was the way they constructed the example. I'm just modifying it slightly here because this takes us back to the language of the first 2 weeks of the class where we were talking about Turing machines, things like that. The same idea is implemented with a Turing machine in my example here. But the basic idea they had was, imagine there's a box with a very, very sensitive photon detector inside, so that even a single photon entering the box, you know, can trigger the bomb. Okay. In our case, it's a Turing machine where if you write, you send in your tape, your input, and it sends out an output, and then in some cases it will trigger the bomb and make it blow up. Okay. So if the Turing machine gets a 1, it will fire the bomb. Okay. And if it gets a 0, it will not fire. Okay. Simple enough, right? And in all cases, it writes the output before it fires, so that we do get the output at the end. Okay. And the question that we have is, we have many, many such boxes. Okay. Imagine that's the situation here. Okay. And some of the Turing machines are missing are their Dutts. Basically, we call those the Dutt boxes. Okay. So we don't have a working Turing machine or a working bomb, whichever way you want to think about it. But in whatever case, what will happen is the input will come out, but the bomb will not explode, right? Okay. So your goal is to find all the working boxes, but obviously without detonating. Okay, you can, if you detonate them, you no longer have a working box and you're also blown up. So we want to avoid that. Okay. Avoid blowing yourself up and also have at the end of it a working box that you know has a bomb that works inside it. So this is the Elitzer-Weidman bomb experiment or bomb problem. Okay. So let us now think about how we could. And we're only allowed to query the Turing machine. You're not allowed to do some other trick. Okay. Where I don't know, maybe you poke a little hole in the box, and and don't let the photon fall on the, whatever. You can think of some. But this is a thought experiment, correct? Right. So we want to be in a situation where we don't have access to other types of information. All we can do is feed the Turing machine, look at the output, and also, of course, we can observe whether the box blew up or not. Okay. Is this problem clear to everyone, the construction of it? Okay. All right. So now let's think about this. So, okay. So let's go the classical way, right? So can we find out which boxes have the working bombs? What would you do? How would you go about it? If you didn't know any quantum mechanics or qubits, about qubits. Prior to, say, 1920s, when we started learning about quantum physics. Or even 1990s, because it took Between 1920 to 1990, there was no progress in quantum computation, right? So it took 70 years for us to like figure out that, oh, we can actually use this for some information processing. So let's talk about the classical world that we knew from before classical computing. So what could you do, right? Find the boxes which have working bombs. Yes?
Find all the ones that don't have working ones and assume the others do.
Yeah, exactly, right? You're kind of stuck. You find the ones that are working, but by working, that means what? What did you do to them?
Stay through the machine.
And then what happens if it's a 1? It blows up, right? So you send in a 1, it blows up. And you're dead, or even if you're far away, somehow you have a bomb that's broke. I mean, you have a box that's exploded. So it's no longer a working bomb. You can send a 0, right? 0 will not blow it up. But then can you distinguish between the dud and the bomb? No. Right? Because the 0 for the dud will also just go through. And so you can't, with the 0 state, you can't distinguish whether it's a working bomb or a dud, right? And the 1 state will distinguish, but unfortunately, as we saw, it will blow up the bombs that we want. So we are screwed, right? Okay, so this is the state. This is, Alan Turing would throw up his hands and say, okay, this bomb, we don't care. I'll go find myself another problem to work on. Okay. But enter our heroine, Kadira. I gave her a name. Cute. Okay. Okay. So Kadira knows quantum physics, and so do you now. Okay. So Kadira comes up with a very ingenious idea. Well, really, there's only one trick in quantum mechanics, as you'll see very soon. Okay. But even when I talk about quantum computing, you'll see really it's just one simple trick. That's what we'll use in every single quantum algorithm. Okay. And the first step of that trick always begins with one thing. What do you think that thing is? We need to create a, yes, superposition. Exactly. That's the one thing we know quantum physics gives us that we don't have in classical physics. So let's start with a superposition. So she sends into the Turing machine the qubit state 1/2, 0 plus 1. Okay. Or actually, in the actual original experiment, we were assuming that we could send photons through, say, some double slit, for example, right? So that the photons don't get observed by the detector unless the detector is in the path, for example, or something like that. I mean, I can go over how the original experiment was conceived, but in our case, we're going to assume we can send a qubit state like this one into it. And if we don't have an explosion, we are going to measure not in the 0-1 basis, but in the plus-minus basis. Okay? So let's remember that. Okay, no explosion, we're going to measure in the plus and minus basis. Okay, so let's go through the cases. So the first case is it's a dud. Okay? Well, the final readout is going to be plus, right? Because you sent in a plus, nothing happened inside the Turing machine. The Turing machine was missing, basically. So the state just went to, right? Everyone okay with that? So you're going to get back, again, state plus, because the measurement of a plus state with a plus basis is always going to be plus with 100% probability according to the principle of quantum measurement. Everyone okay with this? Yes? Okay. Stop me if you're not. Now we take the case of the bomb, okay? Or the working Turing machine. Well, of course, there's a 50% chance the Turing machine sees that one, right? When you measure in this one state, it's going to blow up. When it measures along 0 and 1 basis, basically in this case, that's what the Turing machine is doing. It has a 50% probability it sees the one state, right? And therefore, it'll cause an explosion. So in 50% of the cases, we are going to have an explosion. Okay, so far, not much progress. But now let's look at the 50% cases where the Turing machine sees the cat 0 state. We are safe. The Turing machine will not activate the bomb, and the output state will now be 0. Correct? Coming out of the Turing machine. And remember, I'm measuring this in the plus or minus basis. So there's a 50% probability that I'll get a minus state. Aha. I now have the signature that I was looking for. Because of course, if I just get plus, that just looks like the case of the Dutt. So no, it doesn't differentiate. But the minus state differentiates me from the Dutt case. So that's the signature, the critical signature I'm looking for to know that I have a bomb without exploding it. Okay. So this is our flow chart. Okay. Again, I just wrote it out so that it's absolutely clear to everyone. So I send in the plus state. We get an explosion. Yes, okay, we are dead. But no, we now measure in the plus or minus basis. And did you get plus? If it's yes, then it could be a Dutt or it could be a bomb. We don't know. We still don't have any way to distinguish that case. But if we get a minus, we know it was a bomb and we didn't explode. Okay? Right? And of course, we can work out the probabilities. Right? That's on the next. Any questions on this so far? So we'll summarize the statistics. So if there's a bomb, then there's a 50% chance of explosion, like we said. But if there's no explosion, which is 50% of the time, we now measure in the plus or minus basis. 50% of the time of that, which means 25% overall probability, we'll get a plus, which is not helpful. So that's inconclusive, right? We don't know. But there's another 50% chance, or overall a 25% probability, that now we know that we'll get a minus state. If we get a minus state, we know now that there was a working bomb or working Turing machine. Okay, so we have a 25% chance that we can detect bomb versus Dutt. Now, 25% doesn't seem like great, but relative to the 0% chance, it is infinitely bigger, right? So we made an infinite speed up of our computational problem by simply being able to solve it, right? With 25% of the time. Yes.
So if let's suppose we run this test and we get a plus, so
Yeah.
it's a non-conclusive.
Yeah.
Could I run the test again? And result?
Excellent. Very good. So indeed, you have to do it in a clever way, right? Because you can't measure the plus. Because if you did, then you would be out. You would be done. So you have to somehow recycle the state without measuring it. And repeat this many times. And that, in fact, is the clever idea in some sense. I'll come to that in a minute. But sorry, any questions about this? Okay, so the experimental bomb testing does not look. Yeah, yes.
Can we go over just one more time?
Yeah.
Why a plus means that, like, I'm sorry,
Here or back here? Or?
one more.
Okay, yeah.
There, the final readout is plus with 100% probability. Why is that like definite for a Dutt?
This one?
No, the Dutt case.
The Dutt case. Okay, Dutt case. Well, if you send in a plus state in the Dutt, it just comes out. So when I measure back in the plus or minus basis, I'm always going to get plus. I'm not measuring in the 0-1 basis at the end. I'm measuring in the plus or minus basis. Does that make sense?
I see.
Yeah. So that's the difference. I'm making a measurement not with 0 and 1 at the end, but with plus and minus, which was my original state that I sent in. Yes.
So is it sort of like in the bomb case, the Turing machine seeing 1 or 0 is an additional measurement, and that's
Yeah, it is a measurement. Exactly. So the Turing machine has to measure, right, to know whether it's a 1 or a 0. When it measures a 1, just 50% of the time, it's going to explode. Okay. But when it measures with the 50% probability, it'll see a 0. Because remember, 1 plus is just 1 over root 2, 0 plus 1. Okay. And minus is 1 over root 2, 0 minus 1. Okay. And
in that case, it's not measuring at all. It's just whatever we put in, we're gonna get out.
Which case?
In the Dutt case.
Yeah. in the Dutt case, think of it like the Turing machine is missing. There's nothing in the box to do the measurement. Okay. So this kind of goes back to like when you watch something, it always collapses, right? That's the idea. So if you have a Turing machine that's measuring what the state is, it's always going to collapse it into one state or the other, 0 or 1. Okay. But it has a 50% chance to do either. Okay. And if you are confused, then just remember that a 0 state here, that the 0 state, it can also be written as a superposition of plus and minus. We showed that in the last class. Just like how plus can be written, I mean, it's just, we did that several different ways. We took, different bases and we rewrote the bases in terms of 0 and 1, or rewrote 0 and 1 in terms of the new basis. So that's the thing you have to keep with. Yes.
So we chose the 0 and 1 with improper probabilities. What happens if we reduce the probability of seeing a 1 so the bomb doesn't?
Yeah, very good question. Excellent. So, so in fact, that is the trick behind many of the further experiments that were done, where you can keep reducing the probability enough that you can repeat this cycle enough times to increase the probability that you will detect the bomb. Okay. So that's the basic method that they used in the experiments and in the theories. Yeah. I'll come to that in a minute, but I just wanted to get through the 50% case because that's like the strongest case, in some sense. So, and we can't really analyze the weaker cases yet because we haven't learned linear algebra. Once we do linear algebra, we'll show that we can indeed do those other cases as well. Okay. Okay. Okay, experimental bomb testing. This was an experiment which was carried out in 1995, shortly after Eliotzer and Weidman proposed this. I'm not going to go into the details. Obviously, they didn't explode an actual bomb, but we can represent it sort of by this picture here, which is an interferometer. Remember, in the very first class, I was telling you about like single photon measurements with like Wheeler's choice and so on. Very similar experimental setup, the way they created the single photons, that's why they have these special crystals, but that's experimental details. So they send in single photons, and in their case, the bomb was again whether a beam splitter was in there or not in there. Okay, and they had to tell whether the beam splitter was in there or not in there without actually interacting with that beam splitter. Because if they detected that there was something here, then they knew there was an object, and that was equivalent to exploding the bomb. Okay. So anyway, so their whole goal was to try and do that without actually detecting any clicks in this detector, which would give them which way information, essentially. Okay. I'm not going into the details, but here's a reference to the original paper. So you can look this up and you can read it on your own. It's not that hard to read, especially now that you know a little bit of about quantum qubits and things like that. They don't put it in the language of qubits, but the basic idea is exactly as we have just discussed. So yes, so in that paper, they also proposed and realized this thing that we are all talking about here, which two of you have already brought up, is we can make the probability of explosions go to nearly 0 by reducing sort of the state, by starting with states that are only slightly rotated away. So when you think about it in the blocks here, the plus and minus states are rotated by 90 degrees relative to the 0-1 axis, right? So 0-1 is here and plus minus is along the equator, right? So what if you didn't rotate all the way down to plus minus? If you sent in a state that was only slightly different from the 0-1 basis. Now you have a small probability only of making the 1 measurement, right? Because you're mostly along the 0. Occasionally you go into the 1 with a small probability. And so that's the basic idea. So you start with a state like that. But of course, you don't succeed very often then. And so you have to repeat it many times, and that requires some clever experimental tricks and so on. But the basic idea is that. Okay. And when we do linear algebra, I'll show you that you can work out the math for that pretty easily. Also, as a sort of very interesting corollary or consequence of these ideas, in 2001, Mitchison and Joza is one of the one of the other pioneers in quantum algorithms, they showed that theoretically we could use this idea to make a quantum computer do the calculation without even turning it on. I don't know that I believe this, but it's kind of a theoretical result that you could use a similar idea to like never actually run the quantum computer, but by simply interrogating it in this funny way, right, with a qubit state, that's, you could like get the result out without actually like doing the turning on the quantum computer, actually sending the quantum computer into any kind of state. Okay, we won't cover that today, but or probably in this class ever. But here's a reference to that paper as well. And we can talk about that. That could be maybe an interesting project for a term paper or something like that. Okay, so I'm going to sort of stop talking about quantum measurement and move on to all the other math stuff that we need to cover. But I just wanted to pause here, make sure everybody is on the same page with respect to this bomb detector. Any questions about that or the previous measurement stuff? Because why I'm emphasizing it so much is we're going to use this again and again and again throughout the course. So this basic principle, you need to make sure you understand it. Because really, there's only this one weird trick. That's what we have to work with in quantum mechanics. Okay, if not, let's move on to the next question, which is, or the next principle of qubit states, which did I mention this last time? I don't remember if I did, but if I did anyway, we also want to emphasize that a global phase is irrelevant. That is, what I mean by a global phase is, if I take a state on the block sphere, just call it this state, for example, if I multiply the whole thing by a complex number with unit magnitude, that is any number of the form e to the I theta, okay, it does not change the probabilities. We know that e to the I theta rotates each of the complex numbers, right? Because when I multiply by e to the I theta and I look at the coefficients, I'm multiplying each of those coefficients by that same angle. So in some sense, you can understand that it doesn't overall change the state, basically, because you're multiplying both amplitudes by the same angle or rotating them by the same angle, so they preserve their angle between them. That's what matters. If you think of the two complex numbers that are involved in this qubit state, we are preserving the angles between those complex numbers by multiplying them both by the same angle, okay? Or rotating them both by the same angle. Does that make sense? I'll prove it by like actual proof, but I just wanted to make you think about the geometrical picture as well, okay? So it does not change the probabilities of the state, and that's what we care about, right? We want to make sure that any measurement of this qubit will always, in any basis, right? It has to be not just 0 and 1, but even if I measure along plus or plus I or minus I should get the same answer after multiplying by e to the I theta. So that's what we'll verify now, okay? All right, okay. So let me just lights. Okay. All right, I'll leave that on. It just annoys me because it doesn't automatically know that we have stopped using the video and the PowerPoint. Oh, that nice chart is gone. Should have stolen it. Okay. Wait, if I remember, I can start writing from here, correct? You can all see it over there? Yeah. Oh, okay. Here?
Yeah.
Okay, all right, well. Hopefully, I won't need all this space for this particular. Okay. So we're going to start with the state psi. And since this can be any state, I'll write it as A plus B, where A and B are complex numbers. And A squared plus B squared must be normalized. Okay. So now I take this and I multiply it, I create a new state. And now I want to know that this state is A, normalized. We still want to verify that. But B, it must also have the same probabilities for measurement along any of the bases that we want to look at. I'm only going to do it for two different basis sets. So probability of 0 here is pretty straightforward in the first case. Maybe I should have written that. Probability of 0 here is A squared. Probability of 1 is B squared. Now, let me just, first of all, before we do this, also verify the probabilities to be in the plus state for psi. Okay, so probability of being in the plus state for psi, the state psi. But what I need to do is I need to rewrite psi in terms of plus and minus states. Okay, which I will do by substituting for plus and minus in for 0. That's just plus minus divided by root 2, and then plus b times plus minus divided by root. Okay, so the probability of being in the plus state when I'm in the state psi is just, if I add the terms of plus together, is modulo A plus B squared, or norm A plus B squared, and probability of being in the minus state for the state psi is A minus B the whole square. Okay, so that is for psi. It's this calculation. And now we take the state phi. I've already written it, so I'm just going to find first the probability to be in the state 0 for the state phi. Phi, remember, is completely arbitrary. It's just e to the I theta times the state psi. Okay. Well, pretty clearly that probability is just a e to the I theta, the whole square, which is just modulo a square. Because modulo of e to the I theta is 1, or norm of e to the I theta is 1. Clearly, probability of 1 for the state phi is equal to b e to the I theta squared equals b squared. Now, if we didn't know quantum physics, we would say that's it. We have done, but since we know quantum physics, we know we need to worry about all these other measurement sets, plus and minus, plus I and minus I. For full completeness, I should do it for that as well, but I'm only going to do plus and minus, and you can verify on your own for plus I and minus I. So again, we take the state phi and I rewrite it. Sorry, I should have a little bit. State psi just rewritten in the plus and minus basis. Okay. So the state phi now I'm going to rewrite it in the plus and minus basis. So I put e to the I theta times now the same thing, a plus minus divided by root 2 plus b times plus minus divided by root 2. Okay, bringing together all the terms, the state phi is now equal to AE to the I theta plus BE to the I theta divided by root 2 times plus. Sorry, this should have been. Right? I forgot about the root 2's when I was calculating probabilities. And then this one is AE to the I theta minus BE theta divided by root 2 times. Yes. So as you can see, now the probability of being in the plus state for the state phi is pretty clearly just modulo A plus B e to the I theta divided by root 2 whole squared is just A plus B norm squared divided by 2, which is the same as this one. So this is A plus B norm squared divided by root 2 squared, which is just 2. Okay. And similarly, probability of minus for state phi, the obvious will be A minus B e to the I theta divided by root 2 squared. So, okay, so that pretty much shows our result. We took for completeness, as I said, I should also do plus I and minus I, but you can see the math is going to be nearly identical to the plus and minus state. So you can complete that on your own if you're not convinced. Okay, so what does this mean? So remember when I started out, I said every state psi, every qubit state is given by these two complex numbers A and B, right? And as a complex number, we know every complex number is actually two real numbers, right? So what we have said is that out of those 4 real numbers that we would normally need to specify the state, because A has 2 and B has 2, well, I've just shown you that multiplication by e to the I theta does not matter, right? So what that means is I can always choose A to be real and make B complex. Because as long as I can then pull out a common e to the I theta, let's say A was complex and B was also complex to begin with, I can always pull out some common factor. So by that I mean, here I'll show you what I mean. Let us say that A was in general, let A equal some norm R1 e to the I theta 1, right? Let that be the most general A that we could write down. And similarly, B could be some R2 e to the I theta 2. Okay, just the most general form that I can think of for A and B. And now the state psi, which is written as R1 e to the I theta 1 times 0 plus R2 e to the I theta 2 times 1, well, I can pull out the e to the I theta 1 from this expression, e to the I theta 1 times R1 0 plus R2 e to the I theta 2 minus theta 1. And so you see, I've just shown you that given any two complex numbers, I can always reduce them to the form where it's some global phase e to the I theta 1 times this expression, one of which is a real number and one of which is a complex number. So we've gone from 4 numbers to 1 real number and 2 complex numbers, correct? One real number and 2 numbers that specify this second complex number, right? Because R2 and this factor theta 2 minus theta 1, which I'll call phi, okay? So given those 3 numbers, R1, R2, and phi, this state is fully specified. But we have one more condition on this, which is that the state must be normalized. So we can't just pick any R1 and R2. We must have mod R1 squared plus mod R2 e to the I phi, the whole square equal to 1. which of course e to the I phi is just modulo of that is just 1. So we get R1 squared plus R2 squared is equal to 1. So now we have gone from 4 real numbers, right, to just 2 real numbers. As long as we know, say, one of R1 or R2, we can get the other one, right? And we know, as long as we know phi. Is that okay with everyone? So we are down from 4 real numbers to specify a qubit state to just 2. That's all we need to specify a qubit state. And that's good because that allows us to map it onto the block sphere in very, very quickly. And the basic idea comes from this formula that I was just showing you. We know that R1 squared plus R2 squared, which are both 2 real numbers, must add up to 1. Okay. And we have this angle phi, okay, as well. So if you remember your basic trigonometry, then you know that there's a combination of 2 trigonometric functions that adds up to 1, which is cos squared theta and sine squared theta. So if I set again, and for certain reasons that I won't get into, but if I set R1 equals cosine of theta over 2, okay, that's the only thing that you have to remember is different. I don't choose cos squared theta, I choose cos squared theta over 2 or cosine theta over 2. If I choose R2 equals sine theta over 2. The reason for this comes from some spin physics, spin algebra. So if you take a course in quantum physics, then we can get into it. But just accept for now that we are choosing this angle to be not theta, but cosine theta over 2. Okay. Okay, we are at the end of our sort of journey. We have now written the state psi, the most general state. Remember, we started with just any 2 complex numbers, A and B. From there, we have narrowed it down to just 2 angles, theta and phi. And I've already written down what the number should be. Remember, we can neglect this e to the I theta 1 completely. It's not important for us, right? And therefore, we are left with psi must be equal to cosine theta over 2 times 0 plus sine theta over 2 times e to the I phi 1. Okay, so just two real numbers, theta and phi, are enough to specify my state on the block tree. Any questions on this? Yes.
What is theta in that sort of final state?
Sorry?
What is theta? Is it?
Yeah, I'll show it to you in a minute.
Okay.
I'll show it to you on the block tree. Yes.
So that theta is not the same thing as the equation where we're going to eat the I theta 1, where we originally defined phi to be theta 2 minus theta 1.
Right, yeah, it's just some new theta. Yeah. Which is given by this solution of this equation. That is, I take the real values R1 and R2, right? The numbers R1 and R2, and I find what numbers give me cosine theta over 2 and sine theta over 2. Because we know that the 2 of them must add up to 1. Okay, that's basically summarized in the next couple of slides. So I already shown you that. We have set alpha. In your textbook they use alpha, beta. I use A and B. Doesn't matter. I've just shown you that we can always choose this alpha to be real, beta to be complex, and also my proof is a little different than your textbook. I went to the most general proof. Your textbook just goes through like sort of a special case. So, but now you see the most general situation. Okay, and alpha squared plus beta squared must be equal to 1, as we just said. And so what they do, as I just said in your textbook, is it sets alpha equals cosine theta over 2, beta equals e to the I phi sine theta over 2. So let's do an example with real numbers, and then hopefully it'll become a little bit more clear what to do when you're actually given a state. Okay, let me make sure I don't mess up the numbers on this one. But the basic principle is exactly as I wrote before. So we'll go through it in a little bit of detail. Any questions so far on the general proof? And hopefully I'll do this example and that'll make the general proof. I guess I should have just get the screen. Screen. Is everybody able to see my writing at the back? Sometimes, as I said, I have a tendency to go small. So please let me know what's happening. Don't hesitate to speak up. Okay. Let me just write the number. Psi is 3 plus I root 3 over 4 and 0 minus 1/2. Okay. So the general algorithm I already laid out for you for how to convert this, but let's go through it again. So I'm going to set, if this is A and this is B, I'm going to set A equals R1 e to the I theta 1. Okay, and I need to find R1 and theta 1. So if I set R1 I theta 1 and I have my number 3 plus I root 3 divided by 4. Okay, well, how will I find R1? Given that A is 3 plus I root 3 by 4. What should I do? Anyone? Yes. Euler's formula? Which one? R1 cos theta 1 plus I sin theta 1? Yes? Yes? Right. 3 by 4 plus I 3 over 4. So from this, how do I find, say, R1? Yes. Okay. So compare the imaginary and real coefficients. Here's a real coefficient. Now what? How do I find R1 and theta 1? Anybody else? Yes.
Divide, I don't know.
Yeah.
Divide both sides of the equation equal to each other.
Yeah.
We have 3 over 4 cosine theta 1 equals 3 over 4 sine theta 1 that equal to each other.
What do you mean? So basically you're equating for R1?
Yeah.
Yeah, okay. So that's equivalent to saying I can just divide one equation by the other. Right? So I divide equation. I mean, in case you haven't seen this is polar coordinates basically. So this is how you always solve for polar coordinates, right? You take the two equations and you want to solve for sine theta 1 for theta 1, you just divide 2 by 1. So that gives you tan theta. Equals root 3 over 4 divided by 3 over 4 is 1 over root. So this theta one is clearly pi over 6. Okay. Pi over 3. Take it to pi over 6. Theta. Half 3. Yeah, that's right. Yeah. Sine 30 degrees. What about R1? What do I find that? We haven't found that yet. What should I do? Find R1. Yes? I see a different hand.
Just plug in theta one into the equations.
Sure, you could do that. There's a simpler way. Which everybody who works with complex numbers, which you will be doing, a lot of you should know this way. Yes?
You take the real part.
Real part of A.
They cannot, it would, you say 3 that's 2 cents.
Real part of this, you mean, is R1 cos theta 1 again? I think that's what he's saying too. If you plug in for theta 1, then you can find R1 using the real part, because the real part is R1 cos theta 1. That's what we started out by doing, right? We equated the two sides, the real parts, basically. Yes, yes, you. Norm squared, thank you. Excellent. You should always remember this trick because you'll have to use this often. Whenever you're trying to find the amplitude, right, or the norm of a complex number, then you can just take the square of the real and imaginary parts. And that you can also see here, when I take square of this equation, R1 squared cos squared theta 1 and R1 squared sine squared theta 1, and I add them together, I'm going to get R1 squared. So R1 squared, so 1 squared, oh, I'm getting definitely squeezed down there. Erase this, or I'll leave that there because that's a useful equation. I see, everybody needs to brush up on their complex numbers. Maybe I should have put in some more exercises on complex numbers in the homework. I didn't give you a homework last week because I knew we were going to do I had to get to this real good. Okay, so let me just get through this. So R1 squared cos squared theta 1 plus R1 squared sine squared theta 1 squared sine squared theta 1. So I just take square of both of those equations, and that gives me 3/4 squared plus √3/4 the whole square. Okay, so this side is of course just R1 squared, again because cos squared plus sine squared is 1, and so you get this side 12/16, which is 3/4, which implies R1 equals √3/2. Please remember this because you have to do this often. Okay, this trick, of squaring and adding the sides. And of course, as you did, you can find the angle by just taking the ratio of the two equations. Okay, so now we have expressed psi as R1 e to the I theta 1, right? Minus 1/2 times 1. And if I want to put in what R1 and theta 1 are, it's just e to the I pi over 6, 0 times 0 minus 1/2 times 1. And remember, we want to put it into this format. Cos theta over 2 sine theta over 2, right? So to do that, I will take out the e to the I pi over 6 out of the equation. So I'll be left with √3/2 times 0 minus e to the minus I pi over 6 divided by 2 times 1 times theta. That still isn't quite in the way we want it, because remember we see a plus sign over here, whereas here we have a minus sign. So the last thing we need to use is the famous Euler equation, e to the I pi plus 1 equals 0. That is, e to the I pi equals minus 1. So this -1 here can be written as e to the I pi. Okay, so we get, and I'm going to just neglect this global phase over here, since we know that doesn't matter. So psi equals finally √3/2 times 0 plus 1/2 e, and now I add e to the I pi, I have e to the minus I pi over 6 times 1. So what does this give us? Pi minus pi over 6, right, for the phase. So phi, the angle phi, is simply phi pi over 6. And the other part, which is this part over here, once again, we have to solve for the theta, once again, using the same idea. That is, cosine theta over 2 must be equal to √3/2. Sine theta over 2 must be equal to 1/2. So from this, again, by taking the division of the two equations, I get tan theta over 2 is equal to 1/3. So once again, we see theta over 2 must be equal to pi over 6, and theta must be pi over 3. Okay? Does this make sense to everyone? So writing it down all finally together, our state psi is equal to, again, in this format, cosine theta over 2, 0 plus sine plus e to the I phi, sine theta over 2, 1. But now this theta is now known to us. It is pi over 3, and phi is phi pi over 6. So that was it. And if you're still not sure, we can talk about this outside of lecture, or you can come see me in office hours or whatever. And I do want to try and get to the pre-test today. So let's move on a little bit. Oh. So that was our proof over here. And so now the last question somebody asked me is, what do these angles represent on the block sphere? Well, it turns out with two numbers, theta and phi, they're like latitude and longitude on a sphere, right? You all know latitude and longitude. So that's exactly what we're going to do, okay? So theta is the latitude from the North Pole, right? And phi will be the longitude from the x-axis, okay? Or, I mean, hopefully this drawing makes it clear. So we take theta from the North Pole, just move the point down by that angle, and then rotate it from the x-axis by that angle. Okay, so you can just imagine you start with everything along the z-axis, rotate by theta down here, that's the latitude, and then go away from the x-axis by the angle phi. And that locates our point in the block sphere. So now you know, given any general state psi, how to locate it on the block sphere by finding the angles theta and phi. Everyone okay with this? So I just did that for the state that we wrote down, and it's somewhere over here. That is, it's kind of hard to see, but it's, because theta was pi over 3, so it's making an angle 60 degrees with the z-axis, but phi was phi pi over 6, which is greater than pi over 2. So it's actually pointing sort of into the board in this two-dimensional projection. But on the block sphere, you can see it's in this quadrant of the xy of the equator. Okay? The back quadrant, like. Maybe if I did not so, then, but I don't want to do that right now. So we can also make this a Cartesian coordinate. So we don't have to stick to theta and phi. Given some angles theta and phi, we can locate a point on this in three-dimensional space on the sphere by using something called spherical polar coordinates. Okay. So that is shown here. So first, imagine that we have taken that point, which is over here, and we project it onto the z-axis. The angle between the z-axis and this the state, the qubit state is theta, and this is a right triangle. Okay, that's what a projection does, right? It's projecting at 90 degrees. So in this right triangle, the hypotenuse is this one, which is a radius 1. Remember, because it's on the block sphere, it has to have radius 1. So this is 1. And this angle is theta. So the opposite side will be sine theta. The adjacent side will be cosine theta. And that adjacent side is just the z projection of this point on the block sphere onto the z-axis. So that's the coordinate in the z direction is cosine theta. And now we can do it in the xy plane. So now remember, if I go back to the previous slide, this angle, I mean, this distance was sine theta. That must also be the same as this distance down here. Okay, because that's like the projection of this point onto the xy plane. Okay, and that's the same as this distance over here. That's how far away it is from that origin in the xy direction, in the xy plane. So that must be this same dashed line over here, which is sine theta. And now we can project this onto the x and the y axis. Okay, and again, this angle is phi. Okay, hypotenuse is sine theta. So therefore, this adjacent angle must be cosine phi of that hypotenuse. Right, so the hypotenuse is length sine theta. So this must be sine theta times cosine. And this distance, since it is sine phi relative to the hypotenuse, is sine theta sine phi. That's the y projection. I know it's difficult because you have to think in like sort of three-dimensional axes, and I'm showing it to you on a two-dimensional plane. So you have to sort of mentally make these projections. Hopefully, maybe you have to think about it. But anyway, so now that we know theta and phi for our previous problem, that state that I wrote down, you can find x, y, and z basically. Because we know theta and we know phi, so you can immediately calculate x, y, and z. That's actually how I plotted that point on the block sphere. Okay, by finding the x, y, and z coordinates. Okay, so I am out of time as far as my planned lecture goes. So what I want to do in the next 10-15 minutes is, as I explained in my announcement to all of you, one of the things that we're doing during this course, because this is the first course as well that we are teaching on QCQI, we want to also see how we can improve our educational, the pedagogy of the education. So one of the things we're going to do first is to have you take this pre-test after you've seen this material and see, where we are, and then we can go from there. This will mainly be graded for completeness. Can you just keep passing it? So please try all the problems to the best of your ability, but if you don't know them or you can't, figure it out, that's fine, but we want you to give your best shot at it. Sorry, this will take a while to come back. Sorry, let's see. You didn't get any? There were enough there. Does anybody have extras? Can you pass them back? People got missed. Anybody else need a? Oh, yeah. Anybody else need a copy? Yes. And please put down your name as well, because we're going to track everyone's performance on the test. Not in a bad way, okay? But we want to know how much you learned or whatever, and how we can adjust these teaching. Yes,
Is it fine to use notes on this or is it?
yeah, you can use it.